Alright guys, welcome back. We are on to our final topic for biochemistry, and we're going to be talking about enzymes today. So, before we get into what enzymes are, how they function, they're going to get involved in chemical reactions. So let's take a step back real quick and just remember some important features about chemical reactions. So, when we define a chemical reaction, it's when we're taking one or more substances, pulling their atoms apart, rearranging those atoms and creating one or more new different substances from what we started with. So something like CH4 plus the oxygen, these are your reactants, right? So I've got one carbon to work with, 4 hydrogens, 2 oxygens, and we're going to break the bonds that are going on in these reactants so that I can rearrange them to make the products that are over here, in this case CO2 and water. Okay. But remember that energy is a big part of how chemical reactions progress. So regardless of what chemical reaction I'm looking at, I have to put in energy to break the bonds in the reactants, but then I also get energy back when the bonds reform in my products. So the question then becomes, do I need to invest more energy to break the bonds, or do I get more energy back out when the bonds get formed? So the differential really is how much activation energy do I need as opposed to the payoff energy that comes back out when the bonds form in those products. So remember that activation energy is how much energy I'm required to put in to break the bonds in the reactants. And when we look at reaction graphs, it's really the peak of that graph itself. So we classify your chemical reactions based on how much activation energy you've got going on here. So remember, we looked at these before, right? As opposed to how much energy I get back out. And maybe this isn't the worst thing to relabel once more for yourself. So if I'm looking at an exothermic reaction, here are my reactants, here's my activation energy, and then there's my energy payoff. So I end up netting excess energy when I go through an exothermic reaction. I release more energy as a result of forming the products than I needed to put in to break the bonds in the reactant. That's important because these are the types of chemical reactions that will typically happen relatively quickly, potentially even spontaneously in nature, and so we don't need to put a whole lot of energy in to make them work. Flip side to that are your endothermic reactions, right? So here are my reactants. Here's this huge hump of activation energy that I need to get over, and I only get this little bit off as a payoff in my products, and so overall I have to net inputting more energy than I get out, so energy is absorbed as opposed to released. These are the ones that take a long time to occur, they're slow to start, and they typically end up requiring some other additional assistance to get the amount of energy that they need up front in order to actually run. And a lot of the chemical reactions that are happening in living things end up being these endothermic reactions. And so we're going to talk about where that extra assistance comes from today. And these types of chemical reactions, that extra assistance, is going to come from enzymes. So enzymes are specialized proteins, and they are designed to catalyze or speed up chemical reactions in cells. But the cool thing about them is that they don't get utilized as a reactant or a product. They're sort of just kind of there. And in fact, if you see them in a written chemical formula or chemical equation, a lot of times the enzyme itself is written over top of the arrow. So, I've got my reactants, yield, that's that arrow, remember, my products, and the enzyme is often written over top of that yield sign or that arrow sign, because it's not going to really get directly utilized as a reactant, and I'm not really going to get it back as a product either. We get to recycle it, which is really nice. So, because so many of our chemical reactions that make up our metabolism are slow endothermic processes, these enzymes are going to be really vital to making sure that we can break down those nutrients, create the functional substances that we need to work on a daily basis. So remember that enzymes are going to end in that ASE, right? So when you see those, you know you're talking enzymes. So something like sucrase, lactase, maltase, amylase. And one of the things you'll also notice is that a lot of times they are breaking down sugars, and so they really sort of take that sugar name, add the ASE to the end instead of the OSE, and that's where the names for the enzymes come from, so they get named after what they work on. So, if enzymes are going to help speed up chemical reactions, well, how do they actually do it? Well, your enzymes are going to work by lowering the amount of activation energy that your cells are required to put up in order to make that chemical reaction happen. How do they help do that? Well, sort of think of your enzyme like grandma. Alright, and how many of you have ever gotten that really big squeeze from grandma? You feel like every bone in your body's going to break because she's hugged you so hard. Well, that's kind of like what enzymes do. And enzymes will envelop the substance that they are designed to break apart, and they will put extra strain on the bonds of those reactants, weakening them so that the cell only needs to add a little bit of extra energy to finish the break, as opposed to having to break it from the get-go. So it allows them to use less energy as a result. Another way you can think about it is based on investments, right? So we'll stick with the grandma idea. Let's say that for most of you, you're probably hoping to get your license soon, get that first car, and you've got this part-time job. And in order to put up, let's just say your used car is going to cost you $2,000, well, it's going to take you quite a long time to save up all of that money from your part-time job when you got to pay for your phone and maybe put gas in mom and dad's car to get back and forth from work, you know, so on and so forth. So grandma comes in, like the enzyme comes in, and says, I'll put up half the amount of money that you need for that car so long as, you know, you're keeping up your grades, you keep your job, blah, 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 right? So now you've only got to come up with that $1,000, which is going to happen faster. So the enzyme is not giving up all the energy to make the reaction happen, but it's putting up enough that now the investment that the cell needs to put in as well is a lot less and a lot more manageable, and it's going to allow the chemical reaction to happen much quicker. So this is kind of what we're looking at, right? If I go back to those reaction graphs, I've got my normal energy that I'd have to absorb without the enzyme, right? So like that $2,000 you needed for the car, that's going to take you a certain amount of time to save up before you can go ahead and get that product, in this case your car, or in the case of your cells, some sort of chemical product that they need. Enzyme comes in like grandma, right, and now gives you half the money. You only have to come up with the other half, in which case you get to that peak a lot faster, get to that product a lot faster. So that's kind of how these enzymes are working. They're lowering the amount of investment the cell has to put in while still getting the same product. And those enzymes then get recycled, which is also nice. So here's the interesting thing about enzymes. They are very specific to the molecules that they work on. So when I'm looking at an enzyme and its function, we often use the analogy of a lock and a key. Because you've got all of these enzymes in your cells, but they're all specifically shaped for a particular substrate, a particular reactant that it works on. Which means I'm not going to be able to take a sucrase enzyme, for example, and use it on anything other than sucrose, right? So if I take a look, that enzyme has a very specific shape to the molecule that it works on, just like you're not going to be able to walk up to any house in town and use your house key to open the lock. Your key is specifically shaped for the lock on your house. Alright? So that means every different chemical reaction that goes on in your body, I need a different enzyme for it. And this is why, one of the reasons why proteins are so important in your body, because remember, enzymes are proteins. Okay? So that substrate is kind of like the key, right? It's the specific reactant that the enzyme works on. This is typically how we name those enzymes. And then that enzyme has this very specific shape called its active site, which is kind of like the lock. And that shape of that substrate is specifically shaped for that active site. Once again, going back to protein folding, this is why that folding is as important as it is. Alright, because if the protein isn't folded properly, then that shape is distorted, key doesn't fit in lock, enzyme doesn't break down substrate, and that chemical reaction that it's designed to help move forward doesn't happen. So if I look at sort of a basic cycle for how an enzyme would function. Alright, here's my enzyme, and I've got sucrase as an example here. Active site is specifically shaped, in this case, for the sucrose that it's going to break down. Alright, and the first thing that needs to happen is that sucrose needs to bind to the sucrase itself. Once that binding happens, my enzyme's going to do what we talk about as induced fit, and it literally hugs that substrate and fits it in nice and tight. Alright, puts that extra strain here on this molecule. It's also going to help us bring in some water to go through a hydrolysis reaction, right? And that enzyme's then going to catalyze that hydrolysis reaction, break that bond between the glucose and fructose that used to be sucrose. Once that bond has been broken officially, with the help of the enzyme giving a little bit of the energy and the cell putting in the rest, those products then get released, and guess what? My enzyme looks exactly like it did before any binding happened in the first place, and so this whole cycle can continue to happen over and over and over again. So those enzymes are reusable, which is a really good thing, by the way, because where are you getting all of the material to build these enzymes? Well, enzymes are proteins. Building blocks of proteins are amino acids. So where do the amino acids in your body come from? Well, they come from your diet. So all the protein that you eat on a daily basis, your body breaks down into those individual amino acids, rearranges them, puts them back together, and makes things like enzymes out of them. Well, could you imagine how much you would have to eat on a daily basis to continue ensuring every chemical reaction that needed an enzyme was functional if you had to make an enzyme every single time that chemical reaction was necessary? You'd never stop eating. So the fact that these enzymes are reusable really is an efficiency thing for your body, okay, and allows you to not have to eat 24/7. And even then, I'm not sure that you'd actually be able to compensate for the sheer amount of chemical reactions that needed to happen. So, I mean, eventually these enzymes do sort of wear out, they do get broken, they do get damaged, and they do get replaced. But rather than having to do it every single time you do a chemical reaction, maybe it's every 100 times. It helps to catalyze that reaction instead. And so the fact that those enzymes are reusable is a really good evolutionary efficiency, and really just makes it functional as organisms got bigger, especially.